so we talked a little bit last week, like very, very briefly, on a limit. And that we were going to be talking about limits in calculus. That was about the extent of it. So today we're actually going to be looking at what limits mean. So today we are looking at them from graphs and tables. Tomorrow we'll be looking at them algebraically. So remember that there are 4 representations that we're going to see on our AP test. So those are numbers, so numerically, which is like our tables, graphically, which is graphs, okay? Algebraically, which are going to be our equations, and then verbally, which are going to be like our word problems. Okay? And especially on the non-calculator active portion, that's where you're going to see a lot of like the graphs and tables, okay? Because they want to make sure, they being AP people, want to make sure that you actually understand the concept, okay? And not just I can plug stuff into a formula and go. All right, so that's not really showing understanding of an actual concept, but just shows that you know how to use a formula, which is why we have to be able to manipulate and do things with our different representations. So we are looking at what is the limit of the following function as x approaches 1. Okay? So for us, when we are looking at a limit, okay, your x value is going to be approaching some number. So in this case, it is 1, right? And then our f of x is going to be approaching some other number, okay? Or a y value. So in this case, notice that we are getting closer and closer to that open circle. Now, what is the y value at that open circle? 3. Or at least it looks like it should be 3. Now, our notation for this, we have LIM, which stands for limit, and then we have as x approaches, so it's like a little arrow, and then it's 1. And then we have our function, which in this case is f of x, and then it's going to equal some y value, which in this case is 3. Now, notice that here, we don't have a filled in dot. I don't have an actual value at 1. But as far as the limit is concerned, it's just what y value am I getting really, really, really close to? It doesn't actually have to get there. Does that make sense? So sometimes we'll have holes in our graph. I don't have an actual f of 1 value, but I do have a limit value at that point. Yeah. So, in general, a limit is going to be as x approaches some value c, f of x it's infinitely close to some value L. And again, that notation, we have the limit as x approaches c of f of x equals L. There is kind of a more mathy definition of this, and it uses like deltas and sigmas and things like that. For our purposes, this is going to be good enough. You are not tested on the mathy definition of a limit on the AP test. However, if you continue on into college calculus, they might show you and introduce that. But as far as for us, this is a good enough definition. Okay. So, continuing on. What do we have here? A table, right? So we're going to look at the limit as x approaches 1 this time of f of x. Yes? value gets closer and closer to 1, what does it look like our y values are getting closer and closer to? 3. Now again, it is important to say that technically our tables and graphs are only estimates, because it could technically be like 3.001. We just can't quite see that, which is why tomorrow we're going to look at it algebraically, because those do prove exactly what it is, but we can't estimate from graphs and tables. Alright, so we want to find the limit of the function as x approaches 0. Don't know why that got cut off. Alright, so again, we're looking for some y value, right, as my function my x value gets closer and closer to 0. I want to know what my function value is getting closer and closer and closer to. Yes? And as of right now, we don't have any other way besides graphs and tables. So we are going to use a table. And we're going to use our handy graphing calculator to do so. So you have your calculator. If you did not bring yours, you may borrow one of mine. Just make sure you put an ID or cell phone in there for me, please. An ID or cell phone in there for me. Thank you. And we're all going to follow along the steps as I say them, please. So we're going to make sure our calculator is on. We're going to go to our y equals button. We're going to click alpha and then y equals. And then click enter on number 1. That gives us a Brady fraction. We like Brady fractions. Yep, you're on that one. I have no idea how to do Cassius. Like, I've only ever worked, I mean, I know it can do it, but I have no experience with Cassius. So, I mean, like, I can Google it for you later on, but as far as right this second, I don't know how to do it. Alright, and then we're going to type in an X on top using the button below your mode, and then we're going to type in the square root of X plus 1 minus 1 in our denominator. Are we all able to get our enter on that one? That way it gives us the fraction. Alright. So then, okay, notice, remember that we're wanting to look at values that are close to 0, right? So we want to start our table close to 0. But if you were to go to your table now, most of the time, even if it gives you positive and negatives, it's only going to go up by 1s. And that's not super helpful for us because negative 1 and 1 aren't very close to 0. So if you click your second, which is the blue button, and then a window, that is your table set up. So we want to change the table start to negative 1, but then where it says the little triangle table, that's how much it's going to go up by each time. We want to change that to like 0.1 now instead. And then again, you're going to click second and graph. And now we can get a little bit closer. Okay, so I have a negative 0.1, and that gives us 1.949. And then I have a 0.1. Which gives us 2.049, okay? But as of right now, that's still not close enough for us to see a distinct pattern, okay? So I'm going to go gonna start it at negative 0.1, and I'm gonna have my table step be 0.01, and again go back to second and table. So now, if I make my next value here, negative 0.01, I get 1.995, which shows me a little bit of a clearer pattern. And if I were to make this one 0.01, this is 2.005. So now, by adding in those other two numbers, you do indeed get an error, or it's undefined at 0. Okay. So as I'm getting closer and closer to 0, what does it look like? My y values are approaching here. 2. So we would say the limit as x approaches 0 of f of x equals 2. And you can technically go in and make your steps as small as you want, because again, it's infinitely close, but really you just need to go close enough that we can kind of start to see whatever the pattern is there. Questions on that? Okay. Next up. We want to use our calculator again, okay? So we're using a different function this time. So we have x squared minus 3x plus 2 on top, and an x minus 2 on bottom. This time it gives you the values that it wants you to plug in, which is nice. We are able to get our function put in.
How do we put in the fraction?
Alpha, which is the green button, y equals. And then either click enter or number 1. So at 1.75, we should get 0.75. At 1.9, we should get 0.9. At 2.1, we should get 1.1. And at 2.25, we should get 1.25. Now to get a little bit closer, I would start my table at 1.9 and then put our step at 0.01. So then I get a 0.99 here. And then lastly, we're going to have to change our step to 0.001. If you are already in your table, you can always just click the plus button, and it will let you change the step from the table screen instead of having to go back to that table setup. So here we get 0.999. Here we get 1.001. Here we get 1.01. So what does it look like our limit is getting closer and closer to? 1. How do you feel about using your graph calculator? Okay. Alright. As we continue on, we're going to learn different things like from the graphs, from different functions on our graphing calculator. Because at the end of the day, you want to utilize your graphing calculator on the calculator active portion, so you should not spend excess amount of time doing things that the calculator can do for you on the calculator active portion. Alright, does this limit exist? If so, what is it going for? So what are my y values going towards? On either side of 0. Infinity, yeah? So can I say that this equals positive infinity? Why not?
Because that's technically no limit.
Why?
Because it goes on forever.
But what does that not meet in our limit definition? Yeah, so it says that L has to be a value. Yes. Is infinity a value? No, it's simply a concept or an idea. Now, we can use this notation just to kind of talk about like what's happening as we get closer and closer to 0. So we could put positive infinity there just to say, we're going up and up forever. However, the limit itself does not exist. And the reason is because this is unbounded behavior. Yes? Now, on this next one, it's a little bit different. We're going to look at the graph of this. Anyone know what that graph looks like off the bat? Not that one. Here we go. That one. It is squiggles. Specifically, what kind of squiggles? So I have sine of 1 divided by x. And again, remember that our limit is approaching 0, so we want to get closer and closer to 0. But what happens to our squiggles? They get like faster and faster. Yes, my frequency becomes smaller and smaller and smaller, right? Yes? So again, because they're oscillating between -1 and 1, okay? It never technically goes towards one value, yes? So we would say this does not exist. And the word that we're going to use for these types is called oscillating behavior. Meaning it goes back and forth. Infinitely many times. Yes? Okay. Now the last type that we have, okay, we need to talk a little bit about notation. So remember that when we looked at our tables, right? So like when I was looking at, say, 0, I had to look at negative 0.1 and positive 0.1 because we can get infinitely close from either side of a number. Agreed? Just like for 2, we could look at 1.999, and we could also look at 2.0001. You can always have a left and a right side. And that's what these little symbols mean. So on this first one, it has the limit as x approaches -1 from the left. That's what this little negative means. And on part B, it's the limit as x approaches -1 from the right. So here, I want to look at my graph again, so we can find limits from graphs. We're looking at -1, so we're getting closer and closer to the x value -1, but I want to look at what's happening to the left. So if I follow the graph that is to the left, what y value are we getting closer and closer to here? 1. Now, on the opposite side, if I get closer and closer tracing the right-hand graph, okay, what y value are we going towards from that direction? -2. Yes? So if my left-hand side and my right-hand side don't go towards the same thing, then my overall limit cannot exist. So basically, in order for the limit as x goes to c of f of x to equal L, the limit as x approaches c from the left of f of x must equal L, and the limit from the right of f of x must also equal L. They have to equal the same thing in order for the overall limit to exist. Now, what is h of negative 1? Where's our dot? The negative 1. What's my y value? Where's our filled in dot at 1? Sorry, at negative 1. What's that 1? 1. Do we all see that? The bottom one has an open circle, the top one has a closed circle. So my actual value would be here. So 1. Technically, both of these could have an open circle, and my dot could be up here, right? It's just wherever the dot is, that's my actual value. Now, for my limit, we don't care where the dot is, but for the actual function value, we do care where the dot is. Now, as we go to 3 this time instead, what is our limit from the left? 2. And our limit from the right? 3. Which means that our overall limit does not exist. Now, what is h of 3 this time? 2. Are we all okay with that? Yes. Now, what type of function is h? Piecewise function, yes. Sometimes we might have to graph our piecewise functions ourselves. So we want to find the limit as x goes to 2 from the left and the right, and our overall limit. And we also want to find the limit as x approaches 4 from the left and the right, and our overall limit. But what do we need to do first? Graph it. So remember, the whole point of a piecewise function is that it has restrictions, and we will only graph that piece when it meets that restriction. So on our first piece, what type of graph do we have there? It's a line, okay? Specifically one with an intercept at 3 and a slope of 2. Now, what part of the graph do we care about here? Everything less than, or basically to the left of 2, yes?
Yep.
Now, is that going to be correct? What part's wrong? What do I need there? An open circle, because we do not have an equal to bar. Now, what does the second piece of my graph look like? A quadratic, specifically a quadratic that has been it's been stretched by 2. Yep, it's also been shifted up 1, right? So my vertex would be here. We would go over 1, up 2, over 2, up 8. Then we would go over 3, up a bunch, okay? But what do we care? We care about between 2 and 4? Including 2, but not including 4? Yep. Which means we need what type of dot at 4? Yep. And again, it's going to be rather high up there, so pretending. Yeah, so it's a parabola-like shape that's pretty high, okay? And then what's our last piece look like? It's a V shape because it's an absolute value, and where has it been shifted? Agreed. So our vertex is at 4. And we would get our V shape, but which part of that do we really care about? The right. So remember it has a slope of 1. This time do we have a filled in circle at 4? Yes. Okay, so that would be our graph. And then we want to look at our limits. So what is the limit as x is approaching 2 from the left? Seven. It's 7. Okay, what about 2 from the right? 9. So what does that mean my overall limit does not exist? Okay. What about my limit as f of x approaches 4 from the left? No, it doesn't exist. Remember, the limit can exist even if the dot does not, right? So we would have to figure out what y value is that technically at. Yes. So I would plug in 4 into this one, yes, because that's where that second dot would be. So 4 squared is 16 times 2 is plus 1 gives us 33. So it's way up there. Now, where does it go to on the right?
0.
Now we're at 0. Okay. Which means our overall one does not exist. Yes? Which means that we have 3 different types of problems. Or basically, in other words, where limits do not exist. The first is if our left-handed limit and our right-handed limit do not equal each other. Yes. Our second is like our unbounded behavior, which that was like when we had f of x and we have like some asymptote. So say like x minus 2 squared. If I'm looking at the limit at 2 and it is unbounded, okay, goes on forever. My limit does not exist. And then our last one was when we were looking at something like cosine or sine of 1 divided by x. We have something that is going to oscillate more and more and more as we get closer to 0. So those are the 3 kind of times that we need to be on the lookout that our limit will not exist. And we're going to explore the left-handed limit and the right-handed limit a little bit more further on in the chapter, but for right now, that's just kind of the basis of it. Questions on that?